Bismillahirrahmanirrahim. In the last lecture, dear students, we discussed the sufficient statistics and the jointly sufficient statistics. Now in this lecture we discuss what is the minimal sufficient statistics and what is minimal jointly sufficient statistics. First of all, I discuss what is minimal statistics. What is minimal sufficient statistics? A statistics T, a statistics capital T is a minimal sufficient statistics if capital T is sufficient and is a function of every other sufficient statistics. Dear students, it means T is sufficient. We here discuss only the single statistics, single sufficient minimal statistics. If T is sufficient and is a function of every other sufficient statistics, if it is a function, then we say it is a minimal sufficient statistics. Now we discuss minimal jointly sufficient statistics. A vector capital T which is equal to capital T1, capital T2 up to so on capital Tk of the statistics are minimal sufficient jointly sufficient statistics. This vector is a sufficient minimal jointly statistics if the coordinates of capital T, the coordinates capital T, it's T1, T2 up to so on Tk is the coordinate of that T, are jointly sufficient statistics and it is a function of every other jointly sufficient statistics. It's same just like a single minimal sufficient statistics, mean a capital T is sufficient jointly statistics if is a function, if capital T is a function of every other jointly sufficient statistics with respect to its all the coordinates capital T1, capital T2 up to so on capital Tk. Its note MLE, maximum likelihood estimator, and the sufficient statistics. Let capital T which is equal to small r x1, x2 up to so on xn be a sufficient statistics for theta. Here theta is the perimeter. Then the maximum likelihood estimator of theta head, that is the estimator of perimeter theta, depends on the observation x1, x2 up to so on xn only through the statistics capital T. Furthermore, if theta head is the estimator, is itself a sufficient, then it is minimal sufficient. Dear students, we check only two things. First of all, T is a sufficient statistics for theta. Single T is a sufficient statistics for theta. First one is T is a sufficient statistics for theta. Then maximum MLE, maximum likelihood estimator of theta head of theta, depends on the observation only through the statistics T. If this is a theta head is a sufficient, first of all T is sufficient and then theta head is itself a sufficient, mean two things. First of all, T is sufficient and theta has is also a sufficient, then we can say it is a minimal sufficient statistics, which is theta head. Furthermore, if theta head is a sufficient statistics, then it is a minimal sufficient statistics. Be kept in mind only two things. First of all, capital T, that is sufficient statistics for theta. Also theta head, which says previously MLE, is itself a sufficient. These two things are sufficient, then I say this theta head is a minimal sufficient statistics. The second, here you study only one. Only its statement, but proof is not necessary. If you want to do it proof, then see book Probability and Statistics by Maurice H. de Groot. Next note is Bayes estimator and sufficient statistics. Let T is equal to small r capital X be a sufficient statistics for theta. Then every Bayes estimator theta head of theta depends on the observation, just like the above note, only through the statistics T. Furthermore, if theta head is itself a sufficient, then it is a minimal sufficient statistics. Dear students, only just follow the 2 points in this statement. First of all, capital T is a sufficient statistics, and the second one is only the Bayes estimator theta head of theta depends on the observation, which is also a statistics, capital T, sufficient statistics. If these two things are hold just like above statement, then we say theta head is a minimal sufficient statistics. Same as above, only its statement you have to understand, but proof is not necessary. If you want to do its proof, then see the book Probability and Statistics written by Maurice H. de Groot and check the topic of minimal sufficient statistics. Now next one is the theorem, Fisher factorization theorem. That is, capital T of X is a minimal sufficient statistics if and only if f of theta of X, here theta is the estimator, is the perimeter, sorry, it's the perimeter, theta is the perimeter, over f of theta perimeter up with respect to y is independent of theta if and only if t of X, which is equal to t of y. We take the value from the X and put in the capital T, which is the minimal sufficient statistics, and also take the value of small y from this and put in the minimal sufficient statistics, and you can check these two answers. When we apply T, then answers are same. So this is as a consequence of the Fisher factorization theorem. We use this theorem to solve the problem of the minimal sufficient statistics of any kind. Be kept in mind only this thing, T is minimal sufficient statistics when this is independent of theta, which is its perimeter, if and only if these things are equal. In the first example, normal distribution. You already know that what is the normal distribution for the probability function f of x, which is equal to 1 over 2 pi sigma square root e raised power minus x minus mu whole square over 2 sigma square. We check this normal distribution obeys the minimal sufficient statistics or not by using the criteria of the Fisher factorization theorem of the minimal sufficient statistics. First of all, we put f of x, we put x in this function which is equal to this. We use already the statement in the above from the fraction, and secondly we put small y instead of x. Then these are, now we see these things are equal and cancel out, and other are e is the exponent. Exponent we use e as exp. Then these below from the denominator when goes to up and e raised power this minus this. Now this is the relation of for the only one random variable which is taken from the sample. Now if we take the n randoms variables as a probability distribution function, then we use xn as xn, x as xn and y as yn, which is equal to mean when we put x1 then here is x1 and y1 and y1. Okay? And secondly, if we put x2 here, this is x2 and here this is y2. Mean for x1 this is that, and if we put x1 x2 and y2 then this is also same as, but only difference is x2 and y2. And if we put x3 y3 then same this factor multiply the previous two factors up to so on. When we put xn and yn then these three also up to so on multiplied with this. Now if we compile these all nth observations probability distribution function, then we denote as pi i1 to n exponent, where that is iyi minus mu whole square minus xi minus mu whole square over 2 sigma square. Now if we expand this result xi minus mu whole square, if we expand this and also we expand this, then its result comes to that, which is exponent of that, and these two are cancel out and remaining factor is this. We takes common from 2 mu and from this 2 mu, that is which remains sigma i1 to n xi minus sigma i1 to n yi, and remaining two factors minus sigma xi whole square as it is and yi square with sigma as it is. Now we have to go on our result by using the factorization criteria theorem. If we check the theorem again, in the theorem f of theta x divided by f of theta, that is the parameter y, is independent of theta. We check this factor is independent of theta. Theta may differ from problem to problem. If we takes here, theta varies from problem to problem. Here theta is the parameter, and if we take the normal distribution, then in the normal distribution theta just like as mu and the variance for sigma. Now when we take in this example, in this problem, independent of mu, this factor is independent of mu if and only if sigma xi is equal to sigma yi. Here mu comes in this expression and we comes to is equal to 0 if these two factors is equal to 0, then this mu also equal to 0. Here we make these two factor is equal to 0. First we take equal summation xi which is equal to yi. When these things are equal, then this factor is equal to 0 and mu also equal to 0. Then we say this factor is independent of mu if and only if these two are equal. And secondly, if we take this factor check about its sigma square, that is its standard deviation. We see the standard deviation comes in the denominator of that factor, and when above all the relation numerator is equal to 0, then we say this factor is independent on sigma square. First of all, we check these. When we take these two things are equal, also these two are equal. When these two are equal, then this factor makes 0 and multiply with 0, and also these two are equal, then this is also 0. Fraction 0 over 2 sigma square is equal to 0, and e raised power 0 is equal to 1. Then we say this factor is independent of sigma square if and only if when sigma xi is equal to sigma yi and sigma xi square, which is equal to sigma yi square. So minimal sufficient statistics, that is our required results for the mu, is sigma xi, I from 1 to n, and for sigma square, which is this summation xi and the summation xi square, we take only one thing from, that is we can take xi or the yi, and similarly you can take xi or yi in that problem. Now next is the Poisson distribution, the probability distribution function for the Poisson distribution, which is equal to this f of x, which is equal to p capital X, which is equal to small x, and e raised power minus lambda into lambda raised power x over x factorial. Now first we can check here the problem is check this Poisson distribution is this minimal sufficient statistics or not. We can check the criteria of the sufficient statistics, minimal sufficient statistics, which is the Fisher-Neyman theorem. First of all, we check it for the one sample, f of x over f of y, which is equal to, for the x, e raised power minus lambda raised power small x over x factorial, by similarly f of y multiplied by y factorial over e raised power minus lambda and lambda raised power y. This is for the one sample space, only for x. And now here this expression is for single experiment, single sample space, and now we apply same as it is up to nth, just like above the example, f of xn over f of yn, which is equal to e raised power minus n lambda into lambda raised power summation xi over pi, just like above, yi over this. And here we see e raised power minus n lambda, which is cancelled out with this e raised power minus n lambda. And the next is this after the simplification. Dear students, we check this Poisson distribution is minimal sufficient statistics or not. We have to see only this factor is independent of its perimeter. In the Poisson distribution, the perimeter is lambda. And this factor is independent of that lambda. Only if we take these two things are equal, then lambda raised power 0, which is equal to 1, and this is a constant factor. We make only this thing, we remove lambda from that expression. We can take any problem of any kind, only we have to remove that parameter which is used in the problem. We remove that parameter we say this is independent of lambda if summation xi which is equal to summation yi. So minimal sufficient statistics for lambda is summation xi. You can take summation xi instead of summation yi because these two things are equal. The next example is binomial distribution. Binomial distribution, you already know what is binomial distribution. The probability distribution function for the binomial distribution f of x which is equal to probability of capital X is equal to small x which is equal to that expression. Here q is equal to 1 minus p and x which is starts from 0 to up to so on n. We check this, either this shows a minimal sufficient statistics for its perimeter, here the perimeter is p, or not. First of all, we apply this on a single sample, and this is by using the Fisher factorization theorem for the minimal sufficient statistics which is equal to this expression. And now we put q is equal to now this expression is for the single, and now we take it for the nth samples, f of xn over f of yn which is equal to this. Here nx and y, here we ignore these constants which is independent of perimeter, because here we discuss only the minimal sufficient statistics, and these constants not depend on the perimeter which is this p for the binomial distribution, and we ignore these things. For the nth these are, and if we, the denominator factor is p which is summation yi when goes to up, then its form is this, and similarly for this, here n cancel with small n and the remaining factor is these f of xn over f of yn relation independent of p if and only if these two are equal. If we check these two are equal, mean this factor cancel out and 1 minus p raised power 0, and here also it is equal to 1, and here this factor are equal and which is also equal to 0, and p raised power 0 is equal to 1, and this factor is independent of p when f of x and f of y is equal to. So minimal sufficient statistics for p is summation xi. You can write instead of summation xi as summation yi. Now the fourth problem, which is similar to above three problems, the inverse Gaussian or inverse normal distribution, and its probability distribution function is this. You have to do yourself just like above these problems. If you have any problem to solve this, then you can write your problem in the comment box, then I can solve this problem again also. Now the next is the very important topics starts is the interval estimates. What is interval estimate? An interval estimate describes the range of the values within which a perimeter lies. In the previous lectures we discussed main two things, is the point estimator and the interval estimator. Now the point estimator is closed. Now we start the interval estimator. An interval estimate describes the range of the values within the perimeter lies. Perimeter, we define the perimeter and the statistics and the point estimator in the previous video. You can check these difference and see the previous video. For example, sample 3, 6, 9, 12, 15 and 18 selected from randomly from the population whose mean mu is unknown. Dear students, we select the sample only when we have no population or difficult due to select the population. Then we use some samples from that population to form your work in the steady way. Then x bar is the mean 10.5, that is the point estimate of the mu. On the other hand, if we state that mu lies between x bar minus 1, which is equal to, and when we put the value of x bar 10.5 minus 1, then it is equal to 9.5, and when we add 1, then 11.5, then the range of the values from 9.5 to the 11.5 is the interval estimate of the mu, which is our topic. What is interval estimate? The interval estimate, we first of all we find the point estimate, or we know the point estimate, and then the add 1 in this point estimate and the minus from this estimate, then the interval which makes is the interval estimate of the mu. We may write 9.5 less than or equal to mu less than or equal to 11.5. Now the confidence interval. What is confidence interval? A confidence interval is an interval constructed from a sample values in the behalf that it has specified probability 1 minus alpha of containing the true value of the parameter intended to be estimated. Dear students, confidence interval is the special type of the interval estimator. Confidence interval mean where that interval your answer of that problem lies. And confidence interval is an interval constructed from a sample values. We use these things from the sample values, not from the population, in the belief that it has specified probability. It takes the probability of 1 minus alpha of containing the true values of the parameter intended to be estimated. Here 1 minus alpha is the confidence level or the confidence S coefficient, and simply alpha is the significance level, that is probability of lower confidence level limit less than theta, which is the perimeter of that problem, less than mu u, which is the upper confidence limit, which is equal to 1 minus alpha, and the value of alpha is from 0 to 1, not equal to 0 or 1, and theta is the unknown perimeter. Also, the width of the confidence interval, that is the difference between u minus L, is called the precision of the estimate. U minus L, the upper confidence limit and the lower confidence limit, the difference of that limits is the precision of the estimate. Note, the precision may be increased either by increasing the sample size. If we take the sample size more, then precision is more increased. If or decrease when the confidence level, with the decreasing of the confidence level, when we decrease the confidence level, that is we defined in the previous C, it is noted by C, which is equal to 1 minus lambda. If this decrease, then our precision of the estimate also decrease, and if we increase the sample size, then it is also increase. In the next video, we inshallah discuss its problems, how to confidence interval find out, then you have to more understanding of that topic. Any question you will like to ask, please in the comment section. Okay, Allah Hafiz.